Mark Anderson. I manage both the Manufacturing Solutions Group and the CAM COE Center of Excellence for Saratech. So today we're going to be cramming about 4 hours worth of discussion into a 20-minute high-level overview of this one operation for NX, and this is the variable axis operation. After thinking about this and going through this initial stage, I think I'm going to do this in a series of 4 videos, 4 CES sessions. And after we get into this, you'll see why it needs to be broken up into to be 4 comprehensive videos. One being we need to discuss projection vector in detail. The other is we need to be able to discuss tool axis options in detail. And then the fourth, we have to combine the two because they work off of one another and some conflict with others. So some give certain results, some give other results. So this video here, this is the CES, this is going to be a high-level overview of all 4 areas. And then you will soon to see 3 other segments coming revolving around projection vector, tool axis, and then how to utilize both of them. So for this CES, we're going to talk about what is variable axis. We're going to discuss cut areas. One thing in cut areas that I see quite often in industry is that we don't utilize the parent geometry groups quite often as we should. We're used to just picking the geometry per operation, which creates an excess of screen selection. We're going to briefly discuss drive methods and the characteristics and parameters, projection vector, and what exactly is a projection vector and how it affects the toolpath output. Then we're going to move into the axis and avoidance, its parameters and settings, and then we're going to talk about the strategy tab, where you have several options in there, one of them being the multiple depths. So this is a variable axis dialog. Right now we're talking about the main node, and we're going to specifically talk first about the cut area. Secondly, we're going to talk about the drive method. Third, we're going to talk about projection vector, and then options. So this here is our cut area. So what we see what I've seen in industry is that when people teach themselves how to use NX, or they're going from a very early version of NX, they just do the operation, and then in the upper right hand corner you see they would just specify cut area, and you would go out and select the area that you wanted to cut in the part. So if you had 10 tools that needed to cut that area and you had 30 faces or surfaces within your cut area, you have 300 selections that you need to do before you can process that. So by using cut areas and create geometry groups, as you create that geometry once, you just signify that this is a cut area one time, and then per operation, you just tell it all 300 of those or 100 of those surfaces for every tool. It's just a drop-down menu selection. So it's very important that is used within variable axis, because certain operations, when you go to the next portion of the dialog, it's expecting you to process this in a way that NX likes it to see. Certain operations, they don't require you to specify the cut area first because there's no automatic logic being generated by succeeding through the dialog. With variable axis, there is logic that is being determined in the background, specifically like streamline. If you have automatic drive selection for your curves, cross curves, and your flow curves selected, if you don't have a cut area and you process that streamline dialog, you're going to have to go backwards in the dialog, specify the cut area, go back into the parameters of the streamline for it to automatically try to generate those. So if you do it in the correct process to where you have your cut area first, then you designate the operation, then you process through that operation's parameters. If there's any automatic process taking place, then it can automatically find that information before it processes the dialog. So it's the correct process of NX. So this is our drive method. Your drive method, you see that you have several options. And what I did with this slide is I wanted to highlight which ones were geometry entities and which ones were surfaces, and what the types of parameters each one of these drive methods had. So you see curve point drive method, it relies on exactly that, curves and points. Spiral is looking for a point and a diameter in which to spiral. Boundary is giving it boundaries to work within. Surface area is you're selecting a specific piece of geometry, a surface or a sheet that's designating its flowing capabilities. Streamline works off of flow and cross curves. your radial cut, you're also giving it a boundary. And then contour profile, that is meant for a very specific type, and that is meant to do walls and surfacing along walls. Next would be projection vector. Now we have to discuss what exactly is a projection vector. So think of projection vector as NX's looking point. So when you're projecting the site of NX, you're telling the system, what am I capable of seeing? So if you have your projection vector set correctly, then you'll be able to see all surfaces that you're trying to machine, and then it will give you a tool path regardless of the tool axis that you're choosing. It's the ability for NX to see the object you're trying to machine. You see that the left-hand column, these are dependent on geometry entities, lines and points. And then the right-hand side, these are relative to surfaces or tool axis commands. The relatives, they are always something that you're dictating opposed to something. So relative to drive means normal to drive, then whatever the user wants. Tool axis means the tool axis of the MCS. Tool axis up means the upward facing direction of the tool axis. Surface area, this is where you're going to give it a specific drive method or a specific surface to drive. When you can use this example, and I'll show you an example a little later on in the demonstration, where if you can imagine having a head, a statue of a head on an A-axis machine, a trunnion style machine. If I drew a cylinder around that head and I picked the entire head surface as my cut area, but then I picked that cylinder as my drive, that means that the output on the G code and the style of toolpath that it's going to produce is going to roll the C axis around 90, and it's going to position the tool and it's going to cut with the A axis along the cylinder that I've selected as its drive surface. So then if I built a sphere around that same head and I picked that as my drive surface, now I've unlocked all axes of the machine tool. So I would see full 5-axis motion cutting the head. So you think of drive surfaces are dictating what is able to be moved in the machine. So you can limit it with space, distance, curvatures, things like that, and that will be exactly as the toolpath will be produced as opposed to the surface you're cutting. So it will cut the surface that you told it in the cut area, but it will do it in the drive method type. So here's an example of projection vector per view. So this is a new thing with NX over probably NX 2206. This is very handy for programmers. Before, we had to assume and imagine where we were projecting, which it was very difficult even for seasoned programmers. Excuse me. So now we have this per view, and you'll see that in the per view, you have an option to add more lines. So in this box right here in the very middle where it says projection per view drop down, max vectors to display, it's going to give you 50 vectors. So if you have a very large surface that you need to add more of them for better clarity, then you can add more there and hit the display projection vectors and it'll show you. So the left picture and the picture directly below that, you'll see that those red lines are pointing through the tool axis, and that is what NX is capable of seeing. So now if we had an undercut to that surface, NX would not be able to see it because it's projecting down through that surface. So if we wanted to do an undercut type of area, so for an example on the right-hand two depictions there, the center one I have away from line. So if I was trying to do an internal surface like that with a spherical cutter, that would be sufficient to cut that because none of the two corners have any type of undercutting to it. So imagine yourself standing on that line, walking around the cylinder in a circle. Whatever you're capable of seeing is what's capable of being cut. Now, if I had a circumstance like I have in the right side to where I have those ears at the top, where if I just drew a line down the center of it and I told it away from line, as soon as it got to the undercut side, it would omit toolpath and it wouldn't cut it because it doesn't see that it's capable of cutting it. So at that point, I would need to give it some other type of projection vector so that it was able to see it. So to do that, I would simply be able to put a point there and say away from point. So the difference between line and point is a line is a pole in which you can spin around. A point is a point in which you can orbit around. So from that point, if you put yourself on the point and walked around it infinitely, you would be able to see those ears. So NX would be able to process a toolpath. So that is what projection vector is. Projection vector is what is NX capable of seeing. So here is a depiction of what we have in our tool axis capabilities. So we have some that are a ways and towards line entities and point entities, which is the upper left column. That is what I just showed you, where it's you would either draw a line or select a line on the model saying toward or away. And the toward or away point depicts the back side of the tool. So if you were to do something like away from line, then it would take the tip of the tool and put it toward the line, the tail of the tool away from the line. If you put it toward line, then it would put the tip of the tool on the line, and then any type of motion that it did, it would try to keep the backside of the tool toward the line as well. Same with points. Next one, we have relatives. All of the relatives, no matter if it's vector, part, or fourth axis, or drive, that is always the identifying factor of it being vector, part, relative, 4-axis, or drive, and then whatever the user depicts. So then it would be relative to a vector, you would pick a vector, and then you would manipulate. Relative to part, it would put it normal to part, then relative to your command. 4-axis relative to part, normal to part, relative to your options. Relative to drive, normal to drive, relative to your options. So then normals are exactly that: normal to part, normal fourth axis, normal drive, fourth axis, normal to drive. So you can tell by the options that the fourth axis normal to is activating 2 rotational axis. Fourth axis normal drive activating 2 rotational drives. So normal to and normal to, they're going to try to stay normal to the part regardless of if they activate a fourth or a fifth axis. This is trying to make it to where it is more of a fourth axis rotary type of motion, and the duals are going to be 5-axis motions. But if the normal to part forces out a 5-axis motion, then it's going to be the same as these types of options. Now interpolate vector, interpolate angle, and our part, and interpolate drive. This means that it's not going to be stationary. It's going to be variable. It's going to interpolate from a vector to a vector, interpolate from an angle to an angle, or angle to the part, or angle to the drive. Then I'm going to skip over optimize for a second, and then we're going to go to swarf. Swarf is for that last drive method that we talked about for the contour profile. That's meant for finishing walls and keeping the the side of the tool against a wall. So optimize to drive means that it's going to optimize that tool path to give you a heel and a lead clearance value, so that you can be leading the tool or heeling the tool and not on center of the tool. So it's more of it's an optimized option to your original settings. So access and avoidance, this is where we get into, you have four options. So none obviously does nothing. Now the retract, that's going to, once it goes through your collision settings and what you have in your clearance values, once it hits those values, it's just going to retract and it's going to start a different path, and it's going to omit that area. You have also tilt and retract options. So I would advise people always to use the tilt and retract. It's a safety that's built into NX that if it does find a collision on top of all of your settings that you produced to create your 5-axis toolpath, then it will further advance your toolpath to avoid those collisions, but it will not stop the cutting. And then your fourth option is report collisions. So talking about those, the retract is going to do exactly that, just retract out of there, and you got to watch to make sure the material is cleaned up. Tilt and retract is going to be an automatic setting in the middle dialog that you have options to give it maximum, minimums, and how it's going to react, but it will finish the material. It will finish the cut area unless it absolutely cannot. Report collisions, it's going to do absolutely nothing. It's going to give you a toolpath that collides or gouges or non-cutting move gouges. And then when you go into visualization, or if you run an information on this, it will then list the collisions. So I don't recommend this last option because it takes a very manual process for you to find them. So I would always use the avoidance for tilt and retract. So what I was showing, let me go through this again. So it's very important that we create geometry groups instead of the manual selection process. Because what this does for us is this is 1, 2, 3, 4, 5, 6, 7, 8 surfaces, 9 surfaces, that if I had 5 operations that I had to do to create that surface, I would have each selection, all those selections on screen per operation. So by creating a mill area group, when I create my operation, I have this ready to be selected so that when I go into operations, and any operation that uses data as it's processing the dialogue, like Streamline, if I go into its parameters now with this automatic selection, it is automatically filled out what it dictated was the best flow and cross curves. So now if I do it the manual methodology to where I would just go and create the operation without any type of geometry in there, the dialogue is meant to go top down, left to right. So if I process like I'm supposed to, where it's on main node top down, so what first thing I need to do is I would go in here to my parameters. There's nothing in there. There's nothing for it to pick up. So I would have to go in there and manually do this. Or then I would have to go through and say, okay, these are my cut areas. And the best case scenario is it will process it correctly. But now the next tool, I have to go in there and do the same selection process. So it's better to just create your geometry groups first and then go into attack them with operations. So that is the first part of the demonstration, was your geometry groups. So now if we go in here to this operation, and let's just study how this one itself was processed. It has a surface area drive method, and the drive geometry that it chose was this cone. So this cone, in comparison to this tool's normal axis, that has opened up 5 axis worth of motion. Now, if I would have chose this cylinder as the drive method, or the drive geometry, then it would only allow it to rotate in the A-axis motion. So by your drive geometry, you're dictating what machine axis are capable of making this motion. And that would be indicative of the toolpath that it produces. Now, if we process through this curve point, that's going to require a curve, one line and a curve and a point of where it's going to start and how the motion it's going to take. Spiral, point, and diameter that it's going to go out to. Boundaries, surface area is going to be drive surface. Streamline is flow and cross curve. Well, I won't get into toolpath. That is a highly advanced type of drive method that requires importation of a different a cutter's toolpath. Radio cut and contour profile, this is your swarf. That was the last example. So projection vector, this is where we're saying in our projection vector, how is it being projected normal to drive? So beyond surface area, drive method, this is going to dictate how NX is going to process the toolpath, what type of toolpath it's going to create. Projection vector is it's asking you to give me the correct data for me to see it. So if I had this surface right here that went into a negative, it undercut down here. If I did any kind of projection vector that was up here that was not able to come around and see this, then it's not going to give me a toolpath. It's going to stop. That's why Z-level operations will not do undercutting, because they can't project underneath of them. So in that case, what we could do is we could put a line here and say toward line, and it would be NX looking toward the line, spinning around it, and then we could see underneath there. So that's what projection vector is. So now there's a combination of things that can take place, because these projection vector and tool axis work off of one another at times. So sometimes if you're going to use a projection vector of tool axis, which is straight down from the machine tool, you get into conflict when you try to use some of the tool oriented tool axes. So if you were to do normal to part with a projection vector of normal to part, then that's going to conflict one another, because they're both assuming that some knowledge is going to be derived from a different area. When if they're both at part, then they're both looking at the same piece of data. So there's drive method, projection vector, and tool axis that all work in conjunction for you to get the type of toolpath that you want. So that's why I said in the beginning that this is an operation that really requires 4 different videos. So for this one, we're just going to go over the high level discussion of those 4 points now, and then we will come back. The next video will be strictly over your drive methods. Then the second video will be strictly over tool axis. Then the last video will be over normal on your tool axis capabilities and how they work in conjunction with the other two. So be on the lookout for them over the next couple CES sessions. Okay, now can you see the PowerPoint, or are you just seeing my NX?
I'm just seeing NX.
Okay, let me share the other screen. Okay, so in summary, variable axis operation uses tool axis projection vector and drive settings to develop the toolpath. Your cut area is easier developed in a geometry group and not in the operation itself. Drive method is determining how the machine will be able to move during the machining. Projection vector is how NX sees the geometry. If NX cannot see it, it cannot develop it. And it is best practice, or it's best to use projection preview to get a better understanding of how the tool is looking at that surface. And if you don't see the red arrows going around the surface the way that you expect the toolpath to go, then you're not going to get the toolpath that you want. So before you hit generate on these toolpaths, you want to make sure that your projection preview is giving you the projection vectors that you desire, so that you don't generate in vain. Previously, we had to generate in vain and just keep trying options. The projection preview, it stops all that from happening. Tool axis, it has many settings, and sometimes they correspond to projection vector or drive setting functions. So if you see yourself getting alarms and errors and issues, it's because one is conflicting with the other.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.